Welcome back. Well, I'm now going to do a presentation on how to essentially invert the chain rule or reverse the chain rule because we're doing integration, which is the opposite of taking the derivative. So let's just take a review of what the chain rule told us before. If I wanted to take the derivative of f of g of x, hopefully this doesn't confuse you too much. I'll give another example with a concrete f of x and a concrete g of x. If I want to take the derivative of that, the chain rule just says that the derivative of this composite function is just the derivative of the inside function, g prime of x, times the derivative of the outer, or kind of the parent function, but still having g of x in it, times f prime of g of x. I know this might seem complicated if you aren't too comfortable with this type of notation, but done in kind of an example form, it makes a lot of sense. If I said, what is the derivative of let's say, sine of x squared? Well, in this situation, f of x is sine of x, right? And then g of x is x squared, right? And sine of x squared is essentially f of g of x. So, and this is just a review of the chain rule. You could go watch the video on the chain rule as well, but I don't mind doing a couple problems here. So all this is saying that the derivative of this is you take the derivative of the inside function, g of x in this example, which is 2x, and you multiply it times the derivative of the outer function, or the parent function, and we memorized, I guess, that the derivative of sine of x is cosine of x. So it's times cosine of g of x. So we keep the x squared there, right? If it confuses you, just think about the inside and the outside function. If you take the derivative of kind of this composite function, it's the same thing. That equals the derivative of the inside function, which is 2x, times the derivative of the outside function, but we keep this inside function in it. We keep this x squared there. So that's a review of the chain rule. So what happens if we want to reverse the chain rule? Well, if we wanted to reverse it, we're essentially saying that we want to take the integral of something where we have the derivative of kind of the inner function, and then we have the derivative of a larger composite function, right? I'm just rewriting the chain rule, but I'm writing in an integral form, that this is equal to f of g of x, right? This statement up here is the exact same thing as this statement down here, right? All I did is I took the integral of both sides, right? I'm saying the integral of this is equal to the integral of this right here. I probably shouldn't have switched equal signs like that with you. But let's use this formula, I guess. But all you have to know is this is the reverse of the chain rule to solve some problems. Image invert colors. Okay, so all I said, let's see. Let me rewrite that. The integral, if I have g prime of x times f prime of g of x dx, that is equal to f of g of x. This is just the chain rule in reverse. And I know it's very complicated sometimes when you have it in this notation, but I'll give you a couple of examples. What if I had the integral of, let's say, this is actually one that's often kind of viewed as a trick, but you'll see it's actually not that tricky of a trick. Okay, so let's say I have the natural log squared over x dx. And if you saw an integral like this, you'd probably be daunted, and you'd be surprised. Many people well into college calculus courses are still daunted by this problem. But all you have to recognize is this is the reverse chain rule. Why is this the reverse chain rule? Well, this is the same thing as the integral of 1 over x times the natural log, whoops, this should be NLX, right? The natural log of x squared dx, right? these are the same thing. I just took the 1 over x out. Now this might look a little familiar. Well, what's the derivative of the natural log of x? If you remember from the derivative module, it's 1 over x, right? Let me write that down. Let me write that in the corner here, right? The derivative of the natural log of x is equal to 1 over x, right? So right here, we have the derivative of the natural log of x. So now we can just say that we can essentially treat this natural log of x as kind of a variable by itself. And essentially what I'm going to be doing is I could actually substitute for it. Actually, let's do that. Let's do that. Well, no. I don't want to do that now because that'll confuse you. Although that my flip-flopping is probably confusing you even more. But anyway, I have the derivative of the natural log of x. So I can then say, well, I have the derivative there. So this is a composite function. This is essentially f prime of g of x, right? So then I can say, well, that integral must be equal to this thing. This is something squared, right? So what's the integral of something squared? Well, the integral of something squared is 1/3 that's something to the third power, right? We learned in the previous indefinite integral module, right? And then it's 1/3 something to the third power, and then we know from the chain rule that something is the ln of x. ln of x. And I don't know if I've already forgotten to do it once, but don't forget to do the plus c. Now that you say, Sal, this completely confused me, because it probably did. And if it completely confused you, let's just take the derivative of this, and I think you'll see it happening the other way around, and it might make a little sense. When you take the derivative, we just use the chain rule. You take the derivative of the inside first. The derivative of the inside is 1 over x, and you multiply that times the derivative of the outside function, and then you keep the inside the same. So the derivative of the outside function is 3 times its coefficient, so it's 3 times 1/3 times the whole thing to 1 less exponent. So the whole thing is ln of x. And then, of course, plus 0, right? The derivative of c is 0. Well, this is just equal 3 cancel out. This is equal to 1 over x times the ln of x squared, which is our original problem. Let me do another problem, because I probably started off with something a little bit too hard. What is the integral of, let's say, sine of x to the third power dx? That's often written like this. That's often written like sine of x. Same thing. But I like to think of it this way because it's not a new notation. So, oh, sorry. Actually, this is a mistake. Clearly, I'm making up these problems on the fly. I actually don't want to do that. That is the wrong problem. I want to take the integral, and actually you can see kind of how I'm thinking about these problems. I want to take the integral of cosine of x times cosine of x times the sine of x to the third power dx. Well, we have this kind of more complicated part, the sine of x, and we have the derivative of sine of x, right? Because we learned that the derivative of sine of x is cosine of x. So if we have a function inside of a larger composite function, and we have its derivative, we can just treat this function as kind of like a single entity, and then like as if this was just one variable, right? And then we take the integral of it. So this is just equal to sine of x, and we raise this one more power to the fourth, and we multiply it times 1/4, right? And how did we do that? Because we know that the integral of, say, x to the fourth dx is equal to, x to the third dx is equal to 1/4 x to the fourth. But instead of an x, we had a sine here. And remember, the reason why we did that is because the derivative of the sine function is sitting right here. In the next presentation, I'll show you why this can also be done using substitution, or why they're the same thing. I'll see you in the next presentation.